So let's start the next section where I will talk about open problems in physical mathematics. So here there's going to be a lot more nitty-gritty details of mathematical stuff. Again, we should probably start with an overview of how things are and where we would like them to be. We are going to basically, so there are basically three layers of things that we'd like to have, if you remember from the talk 2 days ago. We have a layer, the most fundamental layer deals with experimental verifiability, the fact that a physical theory needs to be grounded in experimental evidence, and therefore we need the verifiable statements to define our physical theory. And this part, and of course, I forgot to put the pointer options again. There you go. So this part is basically it's basically done in the same way that I consider classical mechanics done. There is probably details that could be done better. But you know, for finite time, I'd rather start working on the other pieces and start putting the other piece in the ballpark. Then there is going to be another piece that I think is needed, which I call information granularity. That is basically the part that should define in general what a physical dimension, what units, and therefore connected measures are. And this is basically just vague ideas. I had a starting ideas a few, like I was able to kind of characterize the problems a few years ago, but I was able to make very little progress. It was also fun because this uses order theory a lot. And then I contacted a professor that wrote a very good book in order theory, basically saying, well, I'm trying to do some of these things. Could you have some hints on what I should be doing and so on? And I didn't hear from him. So I said, okay, you know, that's 90% of the emails like this don't get replied, so it's fine. 3 months later, I have this very short email that basically says, I don't know, it's too difficult or something to that effect, right? I thought about this, but it's a very difficult problem. So, which is interesting because if he replied to me only 3 months later, I suspect that he was thinking about the thing for on and off because the email was sitting in his inbox because he then replied. And so he thought that the problem was interesting, but then at some point he gave up and says, okay, this is too much. And sort of he replied to me so that I'm loading off this problem. I'm not interested on this anymore. So in principle, I think that there is interesting mathematical stuff to be done. It's a little bit, you know, above my level. And then there is also this issue that with this idea of counting states, we saw that I needed non-additive measures, and there was an assumption of additivity here. So maybe that's not exactly what I need. So I just shelved it. And what I'm actually working on right now is a theory of states and processes based on the notion of ensembles. And this is very promising because we have done a lot of results that we saw yesterday, and there are a lot of other open problems there, and so that's what we're mainly going to discuss. I'll give you sort of an overview of what we're trying to do here very quickly, and then we're going to see a lot of the interesting problems that we're trying to solve over there. And those are really at the math level. So if there is anybody here that is really more on the math side, these are really these are a lot of fun. Okay, so first let's go through this information granularity about units and information. And again, the goal is to establish a mathematical precision notion of units, physical dimension, and the required minimal physical assumptions. These are the things that we are actually lacking in math. And a lot of the arguments that we have in reverse physics rely on dimensional analysis and units being treated well. So at some level, we need to do that. And physical dimensions and physical dimensional analysis and so on are a lot more tricky than you would first expect. There are like really a lot of subtleties, and again, it's not clear exactly how you can make a mathematical framework like that. But the idea was basically to have a partial order on all statements, and basically you're going to be able to say, in some sense, this statement is is finer, it's more precise than another or not. And a physical dimension becomes essentially a set of a class of statements that can be compared to each other in a sort of a finite way. So if you have two statements of position, you can compare them and say, oh, this is finer than the other, this gives me more information than the other. But if you have a statement of position and a statement of momentum, you can't compare them. You can't say that one is finer than the other, right? But then you basically need a hierarchy of all of this to be able to sort of define what the physical dimensions are. So some insights, I think, are still valid, and that's kind of why it's sad that I wasn't able to close it. And again, all the notes of all these things are on GitHub, so if somebody wants to resurrect the project, it can actually be resurrected. And so let's look at the basic insight, the things that I do think that are important. So in the topology sigma algebra, it all comes from logical relationships. And so you can say, for example, that the position of the object is between 0 and 1 meters is a narrower statement than the position of the object is between 0 and 1 kilometers, because whenever this is true, this other one is true. So the logical implication essentially tells you that one is valid in fewer cases than the other one. Also, you can say that the third die landed on 1 is a narrower statement that the third die landed on 1 or 2. Again, because essentially this is contained in the other. But note now that this was a statement on geometry. This is a statement in probability. And even this is a statement in information theory. The first bit is 0 and the second bit is 1 is a narrower statement than saying the first bit is 0. So essentially, if a statement is contained in another, then you can compare them through the logic relationship, but that's it. So if you want to say that the position of the object is between 0 and 1 meter is a finer statement, a more precise statement than the position of the object is between 2 and 3 kilometers, you cannot do it through the logical relationship. You need something else. And what is interesting is that this something else is the same, regardless if the precision is a precision in terms of geometry, a precision in terms of probability, and a precision in terms of information theory. Again, this is the whole idea that information is geometry and information is about probability distribution. It's that all these things, they're always the same at a fundamental level. And so again, this is the attempt to say, okay, let's try to find one thing that sort of connects all these aspects. And so the idea is to create, to not only have an operator that allows you to tell you whether something is narrower in this logical sense, but also if something is finer in terms of information content. And the idea is that this has to be a partial order, because you cannot always compare things because they might be about things that are incommensurable. So for example, I could have a statement that tells me this is position and momentum. So these are statements of states in phase space. I can say that, the state is this point. The system is at this point. Or I have the statement P that it's the union of two possible cases, so 2 points. And then I have a C that it's a possible range of position. And I have D that it's a possible range of momentum. And I have E that it's a possible range in position of momentum, right? And so we want to be able to say that A is finer than B, because knowing that I must be at 1 point is more precise than knowing that I can be in 1 or 2 points. B should be more precise than C, and C should be more precise than E. It's finer than E. But we can't compare C and D. Like, there is no sense in which C is finer than D or D is finer than C. And so this basically captures the idea that position and momentum are incommensurable. They are different physical dimensions. Yet the areas of position and momentum can be compared with other areas of position and momentum, and they can be compared with lines in position and lines in momentum. And these are also comparable to points, right? So the issue is that the jump between a line and a surface is going to be some infinite dimensional jump, and that's sort of why you are going to be able to sort of have these classes that sort of work together in this way. And so we would like to basically to say, okay, I have all these statements so that I can all my possible statements on position momentum that correspond to sort of some idealized test procedure. And then you want to be able to choose a unit. I say, you know, A is my units or C is my units and so on. And then you want to be able to find a measure on all the other statements that tell me that, of course, the measure in terms of the unit is 1. And if an object is finer than, if a statement is finer than another statement, then the measure is less. And if two statements are disjoint, are incompatible from each other, then the measure sum. And again, you want to be able to do it regardless of what you take, A as unit, C as unit, or E as unit. So that's sort of conceptually what we would like to do. And again, the concept is simple. The realization, I don't know quite how to do it. So there is some part that the basic notions that we did was essentially copying in some sense or stealing from what De Finetti started in the 19th century with this idea of defining probability from the idea that you can take two events and say, I find this less likely than that, right? So this whole idea of defining probability of the propensity of betting on one to the other was essentially started by him with the idea that you're basically putting a pre-order on these statements mathematically, and then you show on what condition that pre-order becomes in order, then becomes a measure. And so this is essentially what we say. We're going to have some theoretical domain like we had defined from the topologies and the sigma algebra from the verifiable statement. You have a relationship that takes two statements and tells you true or false, right? It tells you whether one is finer than another. You want this to be bounded in the sense that if you have a contingent statement, something that could be true and could be false, then it's always coarser than the impossible statement, the one that always is false, and it's finer than the certainty, the one that is always true, right? So you want this thing to always be in the middle of these two. You want this relationship to be transitive in the sense that if a statement is finer than another statement and the statement 2 is finer than 3, then the first is finer than the third. And you want to have this offset monotonicity, meaning that if you have a statement that it's incompatible with 1 and incompatible with 2, right? Then if S1 is finer than S2, then it must be the case, there is an if and only if, that if you make the disjunction of both statements with the other thing. So if you think in terms of sets, you have a set that is disjoint from two sets, then the measure on the union of the first set with one and first set with the other it has to have the same, I can say, size relationship between the two statements, the two sets by themselves. So essentially, adding a set by a constant should give you the same result. So if you have two statements that are this coarser than the other, and I'm moving them up by the same amount, they are still one coarser than the other. So this is basically what it does. And just with these three things, it turns out that you can prove a lot of things. You can prove that this fineness is a pre-order, which is the type of objects that De Finetti starts with. You can then define equigranular classes, so classes of statements that are all at the same level of information, let's say, than each other. And then you can make a map between the statement and one of these epigranularity class, and this is an order homomorphism, which allows you to do something. So there are a lot of things that they sort of work out, and the nice thing is that these are minimal assumptions, and it gives you many consequences, so it always tells you that you're on the right set and in the right direction. The problem is that we still have no idea to generate how to get to the measure. The main problem, again, you would like to take a unit statement and then define a measure that for every other statement gives you some notion of size. The problem is that you need some conditions for this measure to be unique, and we do not know what those conditions are. And it's clear that you cannot define this on the full space because some of things are going to be incommensurable. So if I took a statement on position, I'm not going to be able to compare it to statement in measurement, so I'm not going to be able to put a measure on those statements. And it's not clear how you define this algebra of comparable statements to the unit and whether that is unique. And so there are a lot of problems that needs to be understood in terms of what are the necessary and sufficient condition. I had actually an undergrad student actually he was quite good, because at the first year he could already like futz around with these things. We actually were able to show that you needed some constraint on the actual topology, like the topology would need to have enough sets to be able to talk about this, because we were able to say, okay, let's take this set, let's throw a lot of let's take this space, throw a lot of things out. Can we still say the same thing that we were able to say before with all the sets and all the points? And the answer was no, you can't. Therefore, you need some of these constraints. So this is sort of a very open problem, and it's sort of at the boundary of logic and measure theory, which probably is not the cup of tea of most people that are watching this, but it's something that again, in principle, I'd like to make some progress on and understand. Now, another thing that I said before is that we need, with physical mathematics, to reconstruct everything. And one of the things that we need is the notion of differentiability that maps well to the math, but also that it's physically meaningful. And this is, again, where we have a prototype that I think works, but needs to be finalized compared to the current literature. I want to have a convenient notation that allows me to do certain things, and I want to be able to see whether the same notion of derivative can be used to generalize a lot of other notion derivatives. I'd like to have one derivative to rule them all. So that's basically the goal. And again, this is it's more on the sort of not pure math in sense of pure math side, but it's more on the math side than on the physics side. One of the things that I already mentioned is that the way that things are defined in differential geometry right now, they're a little bit unintuitive for us physicists. And actually, it seems that they're also unintuitive for a lot of people in the math, because I was at a topology conference once, and I asked the grad students, why are you in topology and not other things? And they said, well, I'm definitely not in differential geometry because all the definitions do not make sense to me. And that was a mathematician that does topology, which is also very abstract. So they didn't make sense to him. So, okay. So like very simply, a differentiable manifold is a manifold that means something that you can sort of chart with real numbers, plus a differentiable structure. And the differentiable structure means that all these these coordinates that you can use have a differentiable transformation among each other. And this definition of differentiability is the notion of the Frechet derivative. That's what you use behind the hood. So you have a notion of differential and a notion of derivative that is based on the Frechet derivative. Then what you do is define vectors as derivation of scalar functions, as we saw yesterday. Basically, the bases become the derivatives, and then you sum these derivatives in a different direction, and that gives you the vector space. And the differentials are linear functions of the vector. So a differential is something that takes a vectors and give you a real number. And so you write things like this. You have the x of v, but v they can write in coordinates, and now this becomes the x component of v. And when you go in, you integrate these differential forms. So you're integrating functions of the vectors. And this sort of does not make sense physically. Like literally, velocity is not a derivation. Momentum is not a function of derivation. Derivations depend on units and cannot be summed, so they don't form a vector space if we give units to the parameters along which we're doing the derivation, which we have to do in physics. So you have two mathematical notion of differentials and sort of way to derive. One that is hidden between the coordinate, among the coordinates, and one that it's defined in here, which I think makes it a little bit strange. And then there is always the idea that in this math things, you define the infinitesimal things like the differentials, and then you define the integration. And we would like to have exactly the opposite in physics. And we have the finite things, and the infinitesimal things are the limit of some decomposition that becomes, there's something that you're getting smaller and smaller. And so what we'd like to have is a notion of differentials and so on that mimics more what's there in so when you do vector calculus and this type of things, the idea of displacements and these type of things that make more sense. And we also want these things to mimic also what happens in variational calculus, which is more similar to the older way of doing differentials and derivatives. And nothing, we would like all these things to mesh together well. Conceptually, the idea is this. Let's say that you have three spaces. You have time, space, and temperature. You're going to have a trajectory, which is a space as a function of time. And then you're going to have temperature, a temperature field, a scalar field, which is the temperature as a function of the position. You want to be able to say that there are some notion of differential of things that are becoming small. And then the velocity is the map that maps an infinitesimal change in time to an infinitesimal change in space, right? So if I give you a small change in time and multiply it by the velocity, I get an infinitesimal change in space. Same thing, this you can think it as the derivative of this function. Now, from a small change in space, you're going to get a small change in temperature. And this is just the gradient. So you see, this is the vector. The vector is something that it's linking this differential to this differential. And this is a covector, but it's still something that is mapping a differential to a differential. And in general, in physics, the idea is that any tensor that we have, like the tensors that we have in special relativity and so on, those types of tensor, they're the one defined on the geometry, are just maps from spaces of differential to spaces of differential. And even the coordinate basis, right, the thing that we think as coordinate basis is not really a vector field, but it's not really a space of vectors that we're doing. We're not summing vectors here. We have differentials that are defined on coordinates, so they're defined on a particular space. And then we have a differential defined on a manifold that it's the unit-free change and go from this point to this point. And the basis, the coordinate basis, is a map that takes an infinitesimal change in the coordinate, the thing that has the unit, and gives you an infinitesimal change on the thing that does not have the coordinate, and it's unit-free. And so if we cast everything in this way, then we can have a notion of differentials, derivative, and tensor that is still mathematically precise, but it maps so much better to the physics, such that when we go and look at the geometry of phase space and all these things, they actually make sense. Like you can look at the symbol and say, okay, I understand what's going on. And this is also the type of thing that I'd like to extend, such that when we work on field theories, We essentially use the same thing with the same notation. It's just that now this space is not just a manifold, but it's a space of function. And it's a spatial function where we're going to be able to define infinitesimal change, and we're going to have functions from a function space to a function space, and we're going to be able to take a derivative because we're going to ask how much this infinitesimal change on the initial space becomes an infinitesimal change in the target space, right? So this is conceptually what I'd like to have. And of course, the problem is defining a set of details that are clever details that allow you to do this. The first clever detail is to basically say, I have these things that I call convergence envelopes. They're a sequence of non-zero elements on R that go to zero. And so these convergence envelopes tells you how you're going to zero when you're making this limit of pieces that become smaller and smaller and smaller. And then you can define a differential as a sequence of vectors such that there exists a convergence envelope such that when you take the limit of the sequence of vectors divided by that convergence envelope, you get a final vectors, which is the tangent vectors. What it means physically is that you can imagine that you're getting these vectors that become smaller and smaller and smaller and smaller, but as they go to zero along a particular direction. For example, they don't keep spiraling out, right? That would not give you a differential in the real space because this limit here would not be defined. The cool thing about defining things like this is that this is the only division that you're going to have. You're not going to have only division with the scalar. So when we're going to, when in the typical way naive way that you define the derivative, you have a division between differentials. We're not dividing a differential between each other, between another. We are defining this differential where you have vectors divided by scalars because we are not going to be able to divide vectors. And the other cool thing is that the only thing that we need here is the vector space structure and the topology that tells me what limits are used. And this is exactly the type of things that one has when you do variational calculus and you work on function spaces because you don't have the manifold structure. And so now you can show that every differential can be seen as a sequence where there is a constant here, which is a tangent vector. There are w's I that go to zero, and you have the convergence envelope. So you basically are rescaling t smaller, 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 but then you have this extra error, right? When you're thinking that you just have t that goes to zero at infinity. And this is how you can think of your differential. You could define it like this, you would get the same thing. And then you can show that you can have this notation that you basically say this is a differential with convergence envelope AI and tangent vector KT. And you can, of course, take the K and move it from the tangent vector to the AI. And this is some useful property that you can use for calculation. What you can then show is that if you fix your AI, you get a vector space. So all these differential make essentially what I would call a tangent space. So the tangent space, it's not the space of derivation, it's the space of these sequences that go to zero in a particular way. And then what you can do is, we're not going to have time to go through the details, but you can define a notion of derivative. And what basically the way that it works is that you have a function that maps a point to a point, a vector to another vector. And when is applied to a differential, you basically, the convergence envelope remains the same. So you go to zero in the same way in the original space and the target space. And the tangent vectors only depend, the final tangent vector only depends on the initial tangent vectors. That's basically what you're requiring. You're mapping a differential from a differential. The convergence, the way that you go to zero is the same, and which direction you go to zero only depends on the initial direction where you were going to zero. And what you can find is that this derivatives must be a linear function. And again, this is interesting because a lot of the generalization of derivatives like Fréchet and others, you kind of have to impose somewhere that they are linear, and we get R for free because we're allowing these essentially to, when you are approaching your point, you can approach it however you want, and that makes the basically the linearity is equivalent to that. You can define a chain rule, and the chain rule becomes simply a function composition. So if you're mapping from first space, second space to third space, or you map directly, and if these two are differentiable, then also the final one is differentiable, and it has to be the composition of the two. And again, what is cool is that the proof goes through very smoothly without very many constraints that you require. You recover the standard notion of derivative from R to R and the notion of the Fauché derivative. And again, you recover this idea that if I have two manifolds and I have local coordinates, I have map between the manifolds, but I can also express the map in local coordinates. And the thing that you recover are the things that you would expect. And as I said before, you have a differential that is coordinate independent. You have differentials on the coordinates that depend on the unit, and the bases are the maps that you use to go from coordinates from differential on coordinates to differential on the space. Again, this is essentially what we do in physics. The vector space structure is here. It's not, and it's among these maps. It's not among these maps and these coefficients as you would expect when you look at this. It's not that this is a basis and these are numbers that we're multiplying the vectors, that they were multiplying the vectors to, because otherwise this dimension would not make sense. This is a map, and we're mapping things from different coordinates. Again, another thing that we kind of talked about yesterday is the idea that differential forms are sort of taking things that are defined on finite regions and dividing them up into infinitesimal pieces. I think that notion of derivative could be adapted to work on here as well. The vector space become the spaces of multi-vectors in some sense. So this would connect to some of the ideas that are there in I forget the name, but the notion of the geometry, the notion of geometry that we were talking about in the first day. But again, I think it's going to map. The whole details needs to be done. So, but let's skip now to the more physical things. But again, if somebody is interested in sort of this foundational question, I'm really trying to find somebody who can help me figure these things out, because I'd like to have, as I said, one derivative to raw, that it's meaningless, and then it's meaningful, that it's physically meaningful, and then we can sort of reinterpret a lot of the things that we have in classical mechanics and classical field theory, E&M, like reinterpret all of that such that we have geometrical notion of what the electromagnetic fields are, how they become tensors in GR, right, and all of this. I'd really like to have those things. But anyway, and everything that we need, as we saw yesterday, we can have this notion of ensembles, and we know that ensembles must have a topology, and the ensembles must mix when we're doing statistical mixtures. Therefore, they give us a convex space. A convex space with a topology, and again, in the literature, there is no literature about topological convex space. There is literature about topological vector space, because that's what they use in analysis, but not about this. So we need basically to bridge this gap to understand how you go from one to the other. And so basically what we're trying to understand here is, first of all, how can we take, what are the necessary sufficient conditions for a topological convex space to embed in a topological vector space, and whether ensemble spaces already satisfy those requirements, or we need some other additional structure that may or may not be true for all physical theories. And then what we want to understand is what the result that are there in topological vector spaces can be generalized to topological convex spaces. My hunch, this should be a lot, but again, it's not a matter of mathematical detail, and yeah. And so let's see what are the things that these things we already saw yesterday, that the use of topology is what allows us to extend the finite combination to infinite one, which is the same thing that one does for topological vector spaces. And we do have, I have a lot of conjectures that I am trying to prove, and we actually have an undergrad right now that is working for me over the summer to see if we can prove them or not. In fact, I think there is a part of this, one of these conjecture that we already proved that it's wrong. But anyway, one of the things, for example, that we would like to understand is if I have a sequence of an infinite mixture that converges, whether I can take out the first element and the thing still converges. Intuitively, it would make sense to me that that's the case, but again, you need to prove it. And the same way that if you have an infinite sequence that converges, can you split it into two separate infinite sequences that converge? Like, I have no idea. Maybe that you can't. I don't know. Another thing is whether if you take a set of ensembles, and then you make all the possible mixture for those ensembles, and then you take all the limits that those ensembles can allow you to have, is whether you are still closed under a convex combination, so that when you make the topological closure, you preserve the closure on the convex structure. Now, this is true for in the vector space. If you take a convex vector, a convex subset in a vector space, and you do the topological closure, you still have something that is convex. And so I kind of think that that's going to happen here in topological convex spaces, but again, it needs to be proved. And one of the ways that you do it is, if you like math, you go and look at what they do in the other spaces and see if you can find a proof that does not use all linear combination, but you can sort of use only the convex combinations to sort of get the same result. Now, yesterday we saw that there are these cancellative convex spaces, and they embed in a vector space. And now the question is, when is this embedding continuously? So can you have a T1 second countable cancellative topological vector space embed non-continuously in a topological vector space? Maybe you can, maybe you can't. If you can't, then it means that as soon as you have a topology on your convex space, and you know that the convex space embeds in a vector space, then you already have a unique topology over there, which would be interesting to know whether that is true or not. And again, one of the things that is true in topological vector space is that finite dimensional topological vector space with the same dimensions are isomorphic in the sense that you have a unique topology. So for example, if you take Rn has a unique topology that makes the sum and the multiplication continuous in that vector space. That is why finite dimensional spaces are so nice, because there is only one possible criteria of convergence, one possible way to essentially define the metric. Everything is nice. When you go to infinity, this is where things become a lot harder. So one of the first things to settle would be, suppose that I have some finite dimensional topological convex space, or a convex space that embeds in a finite dimensional vector space. Do I have a unique topology for the convex space or not? Right? That already is, for example, related to the previous questions in a simpler case. But those are the type of questions that need to be settled. That again, the physical meaning would be that a particular class of ensemble spaces, once they are defined, they would have a single criteria of convergence. It wouldn't matter what the ensemble space is, as long as you can think it of that there are finitely many things that you can mix together. You get you get all this stuff for free. So that would be interesting to know. One other thing that we have identified is that all the bad things seem to be happen at the edges, on the extreme points of the convex space. And the question is whether that's the only thing that bad things that can happen. So if you throw away sort of these edges, everything maybe starts to be nice. I have a suspicion that that's the case, but that's what needs to be proven essentially. So that's part of it. The other thing that we had looked a little bit yesterday is this notion of entropy defines the geometry of the ensemble spaces, and the goal here would be to derive all geometric structure from a definition of entropy. And we saw that in reverse physics, all the geometric structure in physics are related to entropy. And so we want to essentially show that the entropy defines all possible types of geometry that we have on ensemble spaces and also outside of ensemble spaces. We saw that there was this notion of distance that you can define. You take two ensembles and you say, I make an equal mixture of them and I see how much the entropy goes up. This was a nice quantity that it's almost a pseudo distance, but it's also a distance, but it does not satisfy the triangular inequality. What happens is that in both classical and quantum mechanics, this is the Jensen-Shannon divergence, and it's not a distance, but it's the square of the distance function. And so the question is that true for ensemble spaces or for a specific class of ensemble spaces where everything can be decomposed in orthogonal elements? And if this would be true, then again, it would be like a generalization or a result that we were having classical and quantum mechanics, and it would severely constrain the type of spaces that you can have. Another thing that we can do with this distance function, and we can show already with the distance function, is that if you take a point and you make it go an ensemble, as long as it goes closer to this to another ensemble, then this mixing entropy essentially goes to zero and goes to zero in a continuous way. And so the question is whether this mixing entropy recovers the convergence criteria of the space. So it is true that for every sequence of AI that converges to A, and then it is true that the entropy, this mixing entropy, goes to zero. But is the reverse true? So we can prove the in one direction. Can we prove the other side? If this would be the case, then what would happen is that the geometry, like the entropy, this geometry defined by the entropy, also defines the topology based on essentially open ball of entropic distance from different points. And that would very likely give us then a metrizable space. And so we would basically say that all the spaces that are physically relevant are metrizable, and the metric is essentially derivable from the entropy. Now, this is true for classical spaces and quantum spaces. The question is it true for all possible physical theories? And if we had that result, it would be a very strong result that basically would solidify this idea that entropy is geometry. Not only entropy is geometry, but it's exactly the geometry that defines the topology and the criteria of convergence. Now, these are samples of, this is a classical discrete space. This is 1, 2, 3. These are the 3 possible cases. And every point in the triangle becomes a probability distribution. If you are on this side, you have a probability distribution between 1 and 3. If you're in the middle, you have a probability distribution that it's equal, 50% one and 50% the other. So any point in the space here is a distribution between a probability distribution between 3 elements. So A and B are 2 probability distributions, and this is the set of all the other distributions that have this entropic distance less than 0.04. So these are balls, let's say, of a particular defined entropic distance. And what you can see here clearly, these are convex sets. Also, if you do the same thing in quantum mechanics, this is a section of the Bloch sphere, And so every point inside the block sphere is a probability distribution, a mixed state. If you take 2 points, then again, these are the open balls of the entropic distance with the same value. And again, you can see that these are convex sets. Like they don't have a kink like this. If you take 2 points, you always remain inside. And so the conjecture is, are all the entropic open balls convex in classical mechanics and quantum mechanics? Can we actually prove it instead of just drawing pictures? And does this generalize to all possible ensemble spaces? And I tried putting a different entropy function that it never gives you anything orthogonal, and you can come up with things that satisfy the axiom, but they give you balls that are definitely not convex. So probably we can't, with the axiom that we have right now in general, prove that these balls are always convex. But maybe if the space again is orthogonally decomposable, you can always do it. I don't know. That this is the part of things that needs to be understood. And the question of whether it matters is if we had, if we have the topology that is generated by these entropic balls and these are convex, then we have a locally convex topological vector space. It means that we have another set of properties. In fact, the locally convex topological vector space are usually the one where you define derivatives, because derivatives in topological vector spaces that are not locally convex give you some weird features that you do not. So if the entropy not only gave us a geometric metrizable space, but also made sure that the space were locally convex, and then we would be doing a lot of things, and that would be again an interesting physical mathematical result. Another thing that we saw last time is that if you make this distance applied to infinitesimal, you're going to get essentially a metric space. And you're going to have sort of a Riemannian geometry type thing. And we want, again, this to work in infinite dimension. And we would need a way to define this differential in infinite dimension in a way that is consistent, that we would like, that makes physical sense. And so this is sort of a part of the extension of the notion of differentiability. And that's why I want to have a nice notion of differentiability, so that I can say and do these things precisely in the physical mathematical side. And then there are other problems that are even more ill-defined, because a lot of the time in this type of research, defining and finding the right problem is actually the problem. Once you figured out what is it that are the proper axiom and proper starting point, things become easy. So one of the questions is how does the geometry of the space of ensembles relate to the geometry of the spaces of states? So this is completely unclear. Then whether, with this mixing entropy is a number from 0 to 1, it kind of reminds you of an inner product. Does it mean that we always need an inner product in these spaces? So any physical theory has an inner product space. Again, I don't know. And then whether we can generalize some results from entropic geometry to ensemble spaces. So this is sort of some of the pieces that we want to do in information geometry. We want to have a general notion of measure theory. As we saw before, we were able to define this notion of non-additive measures by basically looking for operation in the convex space. In classical probability, you have a probability space with the sample space, a sigma algebra, and a probability measure. You have a state count, which is a measure of the sigma algebra, and then you can define derivatives as essentially probability densities as derivative between the probability and the count of states. And then you can have random variables that are defined on the points, and then you do expectation by integrating the function with respect to the probability, with respect to the state count. Right? This is the structure that we have in essentially in classical theory that is very measure theoretic. And this is exactly the structure that does not work in general for quantum mechanics. And so what we'd like to have is a generalization of this structure that would also work in quantum mechanics, and therefore it would need something that is not an additive measure. One way of looking at this is that when we talk about probability and additive probability is really a probability of outcome. When we do probability in terms of mixing operation, that is something different. And the idea is that the mixing, the measure that we want to define is on this side and not on this side. And so, as we showed yesterday, we can define a state capacity. If I have a set of ensembles, I can say that this set of ensembles is defined on these many distinguishable states by looking at the supremum of the exponential of the entropy of all the possible convex combination, and we can show that this is a non-additive measure. In the same way, you can ask if you have a set of mixtures, a set of ensembles, you want to ask what is the biggest part of this ensemble that I can get from a mixture of these other ensembles. This gives you a coefficient, which we call the fraction capacity. And again, this is a non-additive probability measure in the sense that it goes from 0 to 1 in terms of the value, and it's 1 for the full space. And so we can define on the space of ensembles statistical quantities as those quantities that are linear with respect of a convex combination, and therefore they essentially are expectation values. An expectation value of a mixture is going to be the mixture, the average of the expectation value. And this means that we can have classical operator and quantum operators of expectation value look the same, even though they're implemented differently. In the classical case, it's going to be an integral of some probability distribution. In quantum case, it's going to be the trace of some density operator. But to the sort of more abstract level, these are just linear operations that are real value functions that are linear in terms of the convex mixture. So we can define these in a more abstract way. What still needs to be proved is that we can go the other way around. If we have a classical space and we define a linear operation on the ensembles, can this be represented as the average of something? And it most likely is true, but we need still to do the due diligence. And so once you have this, all of this, you would like to be able to say, okay, I have a state capacity, which is the generalization of the Liouville measure that counts the state. I have the fraction capacity, which is a generalization of my probability measure. I want to be able to define some sort of derivative between the two so that I can define a probability density. And I want to be able to have some sort of integral such that when I take this function and apply it to multiplied by this probability density and I make the integral, I actually am doing the expectation value and recovers the linear operation, so that all linear operator can be written in such a way. I have no idea if this is possible. As I said in the question before, I hoped that the non-additive measure literature would give me a result in terms of these things, but it seems that all the features that we are trying to use do not satisfy the requirement of this. In fact, this is here. There are already non-additive measure theoretic tools. There is fuzzy measure theory. There is a Choquet integral and Sugeno integral that are all defined on fuzzy measure that are a generalization of additive measure to non-additive case. Unfortunately, these don't seem to be the right one, which is sad on one side. On the other side means that it's probably new math to be developed, which probably to be interested, but then I have to find mathematicians that help me to do that. The last thing that we're missing on the ensemble space that I know we are missing are some type of Poisson structure that tells us that we have conjugate variables. I do not have a way to do that right now, and probably it's something that needs an extra axiom, but it needs an extra axiom that is compatible with the things that we're already doing. So very quickly, because we don't have much time, the idea is that both classical mechanics and quantum mechanics is that you are going to have an ensembles and you're moving an ensembles and you have H, that is the generator of a transformation, and T, the parameter of the transformation. You're going to have observables, and you're looking at how the observable change in time. In classical mechanics, you use the Poisson bracket, and in quantum mechanics, you use the commutator. And both of these are skew-symmetric brackets that tell you how variables and observables change during the transformation. So this is what we need to generalize, this idea that we have transformations and conjugate variables and generators and so on. And again, we saw that we have already a way to generalize statistical properties, right? So we have that in the classical case, it would be the integral of the density, and in the quantum case would be the trace of the operator and the density matrix. And so the way that we can generalize the bracket is essentially making the expectation value of the bracket. So on the ensemble space, we define the bracket, the skew-symmetric bracket, that in the classical case should reduce to the Poisson bracket, the expectation of the Poisson bracket, and in the quantum case should be the expectation of the commutator. So this is basically what we like to generalize. And what you can show that this defined in both cases would give you the structure of a Lie algebra. And so this generalized thing, either we derive it or we have to define it to be a Lie algebra, since this is the structure that most likely we're going to have. What it doesn't seem to be, it doesn't seem to be a Poisson bracket, because the Poisson bracket has to act as a derivation on an associative product, and it's not clear to me what the associative product should be, because the expectation of the product is not the product of the expectation. And since we only know how to make operation on expectations, because those are the numbers that we have, those are not going to be the products that the Poisson bracket, for example, sees. And so the question is whether this product can be defined in terms of the generators of composed transformation, and whether the non-commutativity of variables itself can be the non-commutativity of composed transformation, and whether the lack of the relationship between the expectation of the product and the commutativity is what we're looking for. So these are all things that I still have to wrap my head around, and so I'm, it's somebody likes Lie derivatives and Lie algebras and so on. These are the type of things that I'm looking at a more fundamental level. Okay. Right, then it's the question of whether we have an axiom. Right. So one of the way to look at this is that these are both a deterministic and reversible transformation, because they leave the entropy unchanged. So there is a compatibility between this algebra and the entropy itself. And also, this structure guarantees us that there are always stationary ensembles under each deterministic and reversible evolution. So if you have this structure, you can create ensembles that are Boltzmann distributions and are going to be left alone. They are going to be equilibria of the transformation generated by H. And so the question is, can we turn it around? So we already assumed that the ensembles must be equilibria to have an entropy well-defined. He's assuming that every ensemble is a stationary state of some time of evolution, enough to say that there must be this structure, because I will have a generator for my evolution, because I'm in a linear space anyway, so that I can define a Lie algebra like that. And then I want to say every state must be kept the same. Therefore, there must be a quantity whose average cannot be changed, because that quantity is going to tell me that I have these states that are equilibria. And therefore, maybe there is a way to recover this from a more conceptual physical premise that is sort of compatible with all the things that we already said. So anyway, wrapping it up. So it should be clear that we believe that it's possible to create a solid mathematical framework for all of this that starts from these physical axioms. We just need to figure out exactly what these axioms are and how they're structured. And we also need to construct all the needed mathematics from the ground up. So we basically are at topology. We need to build a lot of our things. And to be able to do that, sometimes it means that we're reorganizing core mathematical ideas that are already present in a different way. But sometimes we have to define a new math. So for example, for the differentiability, I think it's more like reorganizing things that we already have. But for topological convex spaces, those do not exist. Though it's a small step, but probably for the non-additive measure theory in the way that we need it, that's probably a much bigger step. That's really new math that needs to be done. And again, we need to span multiple branches of math and physics. So I'm always very interested to talk to people who are more mathematically inclined than me and that can help me guide for this region. And as before, the simplest thing that you can do is sort of fill in this form and say, oh, I know about this type of math, this type of physics, I can help there. And if you instead want to be more involved, you reach out, and then we'll figure out something. And again, this was the hour, so I'll stop.
Right. We've got a couple of questions. So from Daryl, for the measure of granularity, what is the sigma algebra you define the measure on?
So we have a sigma algebra that comes from the experimental domain, which basically are all these statements that are theoretical and stuff. So if all statements are comparable to each other, then that's always going to be the sigma algebra for everything. The issue is when they're not comparable. When they're not comparable, say some statements are statements or positions, some states are momentum, I do not know how to define it. Because in principle, you could say, I start with my unit, my statement that I take as a unit. And of course, the unit is comparable to itself, and I need to be able to give a value for the unit. So I need that. And then you start finding all the other sets and statements that are comparable to it. And then you can grow this sigma algebra. The problem is that there is no there's no we're not able to show that if you with such procedure you would get a unique sigma algebra. You could be that you grow it in one direction, and then some statements now are incompatible with some other statement, though they were still comparable with the unit. So we do not know what are the set of necessary and sufficient conditions to define that sigma algebra. We have some intuitive ideas in simple cases, but how to do it in general, it's not completely clear. Sad.
Next question is from Xinyue. There are multiple ways in differential geometry to introduce tangent vectors as differentials. I think the ones using function germs to define cotangent vector space first are more close to what's being described here. For context, this method also generalizes spatial differential from differential on parameterized path.
Let me look at the thing. Could be. I'm not familiar with that. That's exactly why I was saying that there might be things that are already very similar that have funny names, and so I'm not aware of them. But yeah, I'm not saying that the thing that I'm doing is completely new. I think this trick that makes the derivative automatically linear, it's if not new, at least buried in some paper and nobody's paying attention. But yeah, so this would be the type of work that is needed. Going and look at the literature and see if it exactly is that or not.
Anytime we can find something that's already developed that we weren't aware of, that's great.
Oh, yeah.
Because it saves a lot of work.
Yeah, so this is where, again, I want to use, as I said already, as much as possible things that are already there. If I can just take the math that already exists, but sort of change maybe some symbols so that it's more palatable, I would just do that. Or if you can take it right away as it is, it's also. So topology, most of it, it's fine. Once we just say that it's second countable, anti-zero, it's exactly what we need. Even measure theory is very close. For differentiability, it's a problem of what gets decided to be mainstream, right? So most of the standard differential geometry book use this algebraic notion of tangent space. So that's it.
Next question is from Leandro. The Lie derivative is purely topological. The covariant derivative encodes geometrical information. If I understood correctly, you would like to have a single framework for derivatives, ideally with a notion of derivative which works in all physical cases. Is that correct? If so, to which extent would you like to pursue this search in the context of field theory, given these fundamental distinctions?
Good question. In the way that it's going to work, which I don't know what it is. So the problem with the theory is this notion of the infinite dimension, the infinite dimensional problem, that you have the different criteria of convergence. So what we were able to show, for example, that might be some that might be inside this whole mess. One of the a lot of the ways that one standard trick that it's used on topological vector spaces is essentially to have enough linear functionals that allows you to define the points, and then you have the idea, for example, that you have the states, you have the quantities, the variables, which are going to be linear function of those states of the ensembles. And then you can sort of then also do it twice. The state now is a linear functional of the expectation. And you can do these tricks. And you can do these tricks if you're using essentially the topology induced by the linear functionals, which gives you a certain type of convergence. What we have seen is that the convergence that you at least need for the entropy, because we have this notion of distance, so at least the notion of distance has to be zero. So whatever other criteria of convergence that you have, it has to be stronger than the one that tells you that the entropy goes to zero, is in general stronger than the criteria of convergence that you have on the linear functional themselves. So the thing that is defining probably the geometry, which would be the entropy, is also defining a criteria of convergence that is very strong. And so there is something there that it's all connected, but I don't know what it is. And again, if I had a mathematician that knew all the possible things that I should be looking at, and then we can sit together for like half an hour. Did you look at this? No. Did you look at this? Yes, and so on. Then the whole problem would go on a lot faster. But even with the mathematicians that I talk to and we collaborate with, they are not expert in this subfield, because all these things become very, very technical very, very quickly. And so it's a process. So the question is, right now, I don't know. If you know how to help figure it out, let me know. I'd be gladly happy to have a talk. And also, to be clear, yeah, I'm not a mathematician. So a lot of these things that I do, it's sort of half as a hobbyist, but I still I need to do it with enough technical expertise to at least be able to talk to an expert, so that the expert that I can understand what the expert is telling me, and I can understand what are the problems as they are. But it might be that, me personally, I can bring the problem only up to a level, but then when an expert will have enough understanding, like I will have specified the mathematical problem enough such that there is a unique solution. The problem is always there. Like going back to this quote from Sabine Hossenfelder, like she says, the physicists make a mess of things, and then it's up to the mathematician to clean it up. And it's okay only if you gave to the mathematician enough instruction such that the mathematician can tell you, yeah, I only have one way to clean it up. If you have multiple ways of cleaning it up, then it has to go back to the physicist, and the mathematician has to ask, okay, physicist, in which way do you want me to clean up? Because there are different choices.
Currently no other questions.
let's wait another couple of minutes if people, there you go.
All right, Daryl asks, I think there are notions of convergence that are more general than topology. Topological spaces have a canonical convergence, but there are convergent spaces which do not come from any topological spaces. How do we get the topology from the convergence for entropy balls?
Okay, let me think. Because I stumbled upon this, but I don't remember what I concluded. I don't remember what I concluded. You're right. So I did stumble into this problem, and so the answer was that, let's see. So let's think about it. So we do have a topology, because the topology comes from experimental verifiability. So we are going to have a convergence criteria for the topology. That's sort of, we need to have it because that's what we're getting just by saying that the theory has a basis in evidential, in experimental verifiability. The notion of a topology that the notion of limit that you get from there, it actually is conceptually very sensible, because you have, let's say that you have a limit, right? So you can imagine physically you have something that it's getting closer to something, and then you want to know whether you are you are getting close to that point. And every neighborhood of that point is a verifiable statement that is true if you are in that case. And so what you're basically saying is that, well, you have your sequence of cases that are going closer to the one that is the limit. And therefore, you're going to have a sequence of true false, or whether that verifiable statement is true or false. And what's going to happen if the point is a limit is that at some point that statement is going to become true, and it's always going to become true. So your sequence of points gets to the points where all the verifiable statements are starting to all settle, and they're all going to become the true or false, exactly like if you are in that point. You just need to wait that the sequence sort of goes in, and so I think, to me, that's the sensible way to see to look at convergence. Now, I didn't, so I forgot, like I must have looked at this months ago, and now I completely forgot what was the examples. A further question is that it is a conjecture that the topological series is metrizable. So the conjecture of whether it's metrizable comes from the topological vector space case. So if I have a topological vector space that it's T1 and second countable, it's automatically metrizable. So we have now a topological convex space, right? So a topological vector space. We know that it's T1 because these entropic open ball, you can make them equal to 0, and then that's going to have a singleton, and then therefore that singleton is closed. So you know that every singleton is closed, so you know that you have T1. If it is true, even in convex spaces, that if you have a T1 topological convex space that is second countable, which we must have by axiom, you are metrizable, then we would have a metrizable space, right? So these are the pieces that we need to check. And then if it's metrizable, if I knew that it were metrizable, I think I can prove that the entropic open balls are a basis, are a local basis of the point that you fix as neighbor. So for the Gödel incompleteness spheres, I should probably repeat the questions because the people who are on on YouTube are not going to hear it. So the question is, do you foresee some sort of Gödel incompleteness problem affecting physical mathematics or reverse physics down the line? No, because the way that Gödel's theorem works is that you need to be able to construct a statement that is also about a statement. You basically need to have this recursive nature. And the way that we have structured physical mathematics and all of this is that you have the set of statements, but the meta statements, like the statements that are the physical theory, like that are the ones that connect it to experimental verification. But the meta statements are not of the same type. They are the sort of in the meta language, in the language that you use to describe the theory. They're not elements of the theory themselves. It's like, this is by design because you are not going to be closed with experimental verification when you go on the meta statement. So I might be able to say that to measure whether the mass of the electron is within a certain bound, right? And so that's a statement that has an experimental test associated with it. But if you wanted to ask the question of whether that statement is a certainty, means that it can never be false, right? And that would be an element in the meta language of the theory that we would have. That statement does not have you're not guaranteed experimental verification. In general, when you have the quantifiers, like the for all and there exists, even if you have you're able to make the statement verifiable for one case, once you add the quantifier, you're not necessarily guaranteed that that statement is verifiable or not. So you can say this electron has the mass between these ranges, but then saying, since I know how to measure the mass of an electron, I know how to measure the fact that all electrons have the same mass. That's a leap that it's completely different. So there are a lot of things that you can do in logic when you're assembling statements that you can't do with retaining verifiability. Essentially, the only thing that you can retain while doing verifiability are the finite conjunction and the countable disjunction. You can't do anything else. And if you only have those things, and those are the only things that you're guaranteed to have, you can't construct a Gödel sentence. Like you can't. And so all the things that allow you to define, the numbers and all of that are sort of meta constraints, which are the assumptions from which you derive the set of statements. But then the set of statements that you can have in the theory is still closed in a much smaller way than the Gödel completely would allow you to do. So basically, the way that I put it is that the problem, like the things that you can do with experimental verifiability and experimental verification are so much more constrained and so much less rich that you're going to end up hitting other problems before you can actually hit the Gödel incompleteness theory. So I hope this gives you a sense. It's similar to what we said the other day. The fact that since we don't care about all possible sets, we only care about the sets that can be constructed with this theoretical statement. So the sets that can be associated with an experimental set. Therefore, we only care about the Borel algebra of a topological space. That protects us from the problem in measure theory, the Banach Tarski paradox and all that. So here is the same thing at a logical level. We can do very few things, and therefore you can't construct these paradoxical things because you really can't. You don't have the tools to do it. And again, if there is a mathematician that wants to make this argument precise so that we can make it in a paper, you know, that's also part of the things that we can do. Let's give it another half a minute to see if there's anybody else who is. You also need the time to come up with questions and digest all the hundreds of things that I've thrown at. Okay, we close it here then. Thank you for all of you guys for having stayed up to this time. And again, if anybody else wants to be more involved, let me know. We have the Discord where we can discuss some of these things. If somebody wants to have some follow-up discussions on a live so that we can actually talk in person and not just for a chat, I'm welcome to do it. And if you tell other people that this project exists, that would also be useful. And thanks again.